Imagine you want a nice cup of coffee. You don't need to understand how the coffee machine works inside. You just press a button and voila, your coffee is served. That's pretty much how an API, or application programming interface, works. It's like the coffee machine. You just press buttons and it delivers results without requiring you to understand all the inner mechanisms. The only thing you need to know in order to achieve your goal is what the inputs and outputs are. In this video, we'll dive into the Tudatpy API Reference, which is like the user manual for this coffee machine. It's a detailed guidebook that lists all the essential parts of Tudatpy, its modules, submodules, functions, enumerations, and classes. This manual might seem a bit tricky to navigate at first, but don't worry, by the end of this tutorial you will hopefully feel more confident and ready to make the most out of this powerful tool. I've opened the Tudatpy API Reference page in my browser, and you can find the link in the description. On first look, two key sections stand out. On the left side of the page, there's a search bar, followed by a list of modules. Meanwhile, the main body of the page mirrors this list but offers more detailed information. Let's focus on the left part and take a look at the modules. First of all, what is a module? You should think of a module as toolboxes in Tudatpy. Each module contains a set of tools, functions, classes, enumerations that are designed to perform specific tasks. For example, one module might handle trajectory calculations while another deals with numerical integration. And this is exactly what we see here. If we take a look at our modules, we see the ASTRO module, the constants module, data, interface, math, numerical simulation, trajectory design, plotting, and utilities. Let's take a look, for example, to the ASTRO module. As you can see here, the ASTRO module is made of submodules that are frame conversion, element conversion. You could expect that the frame conversion submodule of the ASTRO module will allow you to switch and to go from one reference frame to the other, or that the element conversion submodule will help you converting a Cartesian state into a geodetic state, for example. This list over here is quite intuitive, and I really invite you to take a look at it. It also gives you an idea of what you can do with Tudat. It's a good starting point for you in order to know what modules and submodules you need to use for your task. We can open another module and see what it contains. For example, the numerical simulation module contains the estimation setup, the environment setup, propagation setup, estimation, environment, and propagation. These are submodules that allow you to do specific things such as setting up your estimation or the environment or the propagation. For example, in the propagation setup, you might expect to find a way to define accelerations acting on a body when it comes to propagate its orbit. Let's explore the ASTRO module together. The API reference tells us that this module is designed for fundamental astrodynamics calculations. A good example is the frame conversion submodule, which provides tools to convert between different reference frames. You may also find some theoretical explanations and literature included to add context. But the interesting part is in the functions section. This area lists the functions available for frame conversion, each with a brief description of its purpose. Take the first function, for example, rotate state to frame. This function allows you to rotate a Cartesian state into another frame, let's call it frame B, using a rotation matrix and its derivative. So how do we use it? The Tudatpy API reference makes it straightforward. If you click on the function link, you are taken to a page filled with technical details. Let's try to break it down. The function name, rotate state to frame, is followed by brackets that list its input arguments: original state, rotation matrix derivative. The API specifies that these inputs must be NumPy n-dimensional arrays, as you can see here. After the brackets, there is a right pointing arrow indicating that the output is again a NumPy n-dimensional array. So as you can see, you have inputs, and then you have a right arrow and the output type. The parameters and return sections clarify everything with more human-friendly explanations of the inputs and the outputs. For example, we can see that the original state must be an n-dimensional array, in this case of a fixed length, which is 6 by 1. So in other words, just like when making coffee, we need some ingredients to have this function work properly: the original state, the rotation matrix, and its derivative. One thing that you might notice if you read through the parameters section is that the rotation matrix time derivative is set by default as a matrix made of zeros, which means that if you don't specify the rotation matrix time derivative, then Tudat will assume that the matrix is not changing over time. This function was quite straightforward, as both input and output types were simply NumPy arrays. Now let's explore a different function. Let's navigate to the numerical simulation module, specifically into the estimation setup submodule, and let's click on the observation submodule. And we see that this module contains a set of factory functions for setting up the observation models, and here we see another list of functions. Let's take the first one, for example. It's a link definition, and the API reference is telling us this is a function to create a link definition object. We click on the link. We can see that this function, as specified by the Tudatpy API reference, is taking as input argument just the link ends. This is actually a dictionary where the keys are of a type called link end type, and the values are of a type called link end ID. At this stage, it's not crucial to fully understand what a link end type or link end ID is, but all you need to know is that the input must adhere to this specific structure, defined within Tudat. Just like strings, arrays, and floats are types, these are also predefined Tudat types. If you try to use a dictionary with simple strings as keys and NumPy arrays as values, the link definition function will throw an error because it's not the expected format. It's expecting you to provide a dictionary where the keys are the link end types and the values are the link end IDs. The output of this function, indicated right after the arrow, is a link definition object. So in the future, you might come across Tudatpy functions that require a link definition object as input. When that happens, you'll know that you can use the link definition function to generate the necessary input type required by your function. You should use the list of modules and submodules as a roadmap. Each level in the list represents a step on your journey to the function you want to use. By following this structure, you naturally arrive at the correct syntax for writing the code. For instance, let's suppose you want to use the function rotate state to frame. Let's go back to it. So it was in the Astro module under the frame conversion submodule, and it was like our first function. Let's suppose you want to use this function. How do you do that? As we just saw, it was in Astro frame conversion and then you find your function, rotate to frame. So when writing the code, you are essentially retracting this path in reverse, telling Python exactly where to find the function. And so you will need to write something like this. First of all, we import tudatpy.astro as astro. This is basically us accessing the astro module that we have seen in the Tudatpy API reference. We will also need numpy because, as if you remember correctly, the rotate state to frame inputs were required to be of a specific type, and that type was defined as numpy n-dimensional array. And we just act with the code. We write the simplest code we can, so we select a Cartesian state, a random one. I've chosen this one, 1 0 0 1 0 0, and we select a rotation matrix, and I've chosen a very simple one, which is the identity matrix. And then we are basically done. We access Astro, then we access its submodule, frame conversion. That's the submodule we need. And within that submodule, we access the rotate state to frame function, which takes as inputs the Cartesian state we have defined as a numpy array of 1 0 0 1 0 0, and the corresponding rotation matrix, which in our case is the identity. We could also add a third input, which will be the derivative of our rotation matrix. But if we don't write anything, we know that Tudat will use a null derivative for our rotation matrix, basically, as a default. So, and in the end, we can print the rotated state, and what we are expecting to find is that if everything works correctly, is that what we get is the Cartesian state we have defined, because we are basically not doing anything to our state, since we are just acting upon it with the identity matrix, which means there's no rotation after all. So let's run this code. As you can see, I ran the code by giving the command Python and the name of, the path of my function, my little function, which is called snippet rotate state to frame.py. And as you can see, on the left side, we have as an output a numpy array of that is basically our initial Cartesian state, because we didn't change it actually, we just rotated by the identity matrix. So this validates our result, and if we want, we can write out the type of this array. Let's check it. So here I changed the code just for the sake of showing that the type that was returned by our Tudat function, rotate state to frame, is indeed what the Tudatpy API reference is telling you, which is a numpy n-dimensional array. So you have it here. I hope this clarifies the connection between what you see in the API reference and then how to use that information within a Tudatpy code of your own. Thanks for staying with me, and I'll see you next time.